Hi everyone. Today let's talk about session 12.8, maximum and minimum problems. Local extremums. A function of two variables f of xy has a local maximum at ab if f of xy less than or equal to f of ab whenever xy is near ab. So the picture is like this. Okay, so AB is the highest point. So when f is near AB, f of xy is less than or equal to this point. Okay, so then we have a local maximum. A function of two variables have a local minimum if f of xy is greater or equal to f of ab whenever xy is near ab. Well, then the picture looks like this point, right? The points near it is greater or equal to this point. Then this guy is a local minimum. Assuming that the partial derivatives of f are defined everywhere, how do we search for the possible locations AB where local extremas can occur? Well, do you remember in Calculus 1, we also have a local maximum, local minimum. They occur at the critical point. Critical point corresponds to the let me draw it here. So local max, local mean in Cal 1. Critical points means the derivative, the first derivative is either 0 or does not exist. Okay, so critical points, they're first in the domain, and then f prime of c is 0 or f prime of c does not exist. Okay, if f is differentiable, then the derivative must be 0. Okay, here, similar to that. At a local maximum, okay, if we suppose the partial derivatives are defined everywhere and continuous, then what can you say? Can you see the tangent plane is horizontal? Horizontal. Okay, and here you see this tangent plane is horizontal. So in either cases, the partial derivative with respect to x is 0. The partial derivative with respect to y is also 0. So for a function whose partial derivatives are defined everywhere, the only possible location for the local extremas are those at which the gradient vectors equals 0. Okay? Because remember what's the gradient vector? That is partial x and partial y. At points AB such that the gradient vector equal to the 0 vector is called a critical point of f of xy. Okay? But be careful, not all critical points give local maxima or local minima. A saddle point is a critical point, but it's neither local maxima nor local minima. Okay, you can see near this guy, there's some point that is above it, there's some point that is below it, right? So, but at the saddle points, both partial f partial x and partial f partial y are 0. And notice local extremas do not always come as isolated points. Okay, unlike Cal 1, the saddle point is always the isolated point, but now it's not the case. The local extrema could be a line, right? Like this picture, you see? If we have like a cylinder, then the local minima is the whole line at the bottom. Okay. Yeah, so exactly. This is the parabola. The graph is parabolic cylinder. Okay, flow. And all points xy along the line in the xy plane are local minima. So, okay, let's. Okay. So review second order partial derivatives and the Hessian. So we call that the notation used for the second order partial derivatives are fxx, fyy, fxy, and fyx, right? And sometimes, I mean, most of the case, the mixed partials are equal, okay? If the domain is open and the second order partial derivatives are continuous, okay? All the second order partial derivatives of a function can be collected in a 2x2 matrix called the Hessian matrix for f. So we denote this matrix by H for Hessian, okay? So the order is fxx, fxy, fyx, and fyy. Okay, the Clairaut's theorem, equality for mixed partials. Yeah, so we assume the mixed partials are defined and continuous on the domain, and that domain need to be open, okay? Open region in R2. Then for all the xy, we have the mixed partial equals. Okay, example. Let f of xy equals this guy, find the Hessian matrix. Okay. So let's see. Fx equals derivative with respect to x, 3 times 4, 12 x cubed. And then derivative of x is just 1. We have 2 e to the y. Fy, first term has no y, so it's gone. And then derivative of e to the y is e to the y. And don't forget the constant multiple, 2x in front. Okay, now what is fxx? Okay, so take the derivative of fx with respect to x, 3 times 12, 36x squared, and second term has no x, so it's gone. Fyy. Okay, take the derivative of e to the y is e to the y, so 2xy. How about fxy? Wow, let's see here. To the derivative of fx with respect to y, we have first guy has no y, so it's gone. Second guy we have 2e to the y. Okay, and you can see this is the same as fyx. Okay, so the Hessian matrix equals fxx, 36x squared, fxy, 2e to the y, fyx is the same, 2e to the y, and fyy, 2x e to the y. So this is Hessian matrix. So far so good, everybody? Okay, how do we analyze critical points? So let's recall some quadratic approximation and the secondary test from Cal 1 and Cal 2. Okay. And so Cal 2, we talk about the Taylor polynomial of degree n, right? So instead of just linear approximation, we can have quadratic approximation. So let f be a differentiable function of one variable. Assume that x equals to a is a critical point. Well, because it's a critical point and because f is differentiable, it means the derivative at a must be 0. Okay. Using Taylor series, we get a quadratic approximation. It's f of a. So remember the Taylor okay. Polynomial. Oh, why is it shifting my stuff? That's interesting. Okay, let's see. So that's okay, it's not shifting. Okay, so k from 0 to n, we have the k derivative over k factorial times x minus a to the power of k, right? So here we should have f prime of a times x minus a, but because f prime of a is 0, so that's why you see this term is gone. Okay, then this is the quadratic approximation. Okay. Now, so we can look at this term, right? Look at this point, right? You can see this point is a local maximum, okay? And you can see this guy, the shape is concave down. Okay, and this is a local minimum, and the shape is concave up, right? If it looks like an umbrella, then it's concave down. If it looks like a bow, then it's concave up. Okay, but the error of the quadratic approximation on the right-hand side is not negligible if the second derivative is 0. That's why the second derivative test is inconclusive when the second derivative is 0. Okay, so here are the examples. The second derivative of all of them are 0, but you can see the points can be a local max or local min or saddle points. So neither local max nor local min. Okay, so that's why the second derivative test is inconclusive when the second derivative is 0. Okay, so if the second derivative is positive, then the quadratic approximation is an upward opening parabola. Okay, therefore f of x attains a local minimum at x equals a. Okay, why is that? Let's go back. This is a quadratic approximation, quadratic function, right? And we look at the coefficients, okay, the leading coefficients. If it's positive, then the parabola opens up. If it opens up, then we have a local minimum, right? Okay, so let's put it here because the leading coefficients open up. We know a parabola, if it's opened up, this is the local mean. Okay, if the second derivative is negative, then we have the parabola opens down, then we have a local max in this case. So far so good. And if the second derivative is 0, then the quadratic approximation is constant. It means the quadratic approximation does not help us to determine there's a local maximum, minimum, or neither at x equals a. So you need to go to what higher terms, okay? So you need to look at, think about it. If this guy is also 0, then you want to consider more terms in the Taylor polynomials. Okay, maybe a higher degree will work in this case. Okay, so that's why second derivative test is inconclusive. So this is the idea from Calculus 1 and Calculus 2 and how the second derivative tests work. Now let's generalize this idea to higher dimension. Okay, so let's look at the quadratic approximation, and the second derivative for f is a function of x and y, so two independent variables. Let f be a function of x and y. Let AB be a critical point. Using Taylor series of two variables, which is not in this class. Okay, I know you haven't learned it. Just accept the fact this. But if you want to know more, please come to my office, and I'm happy to show you. Okay. So this is the Taylor series of functions with two variables. The quadratic approximation equals because it's critical points, so we have fx of AB is 0 and f partial y AB is also 0. Okay, so we have f of AB, and then we don't have the first derivative terms because partial f partial x is 0, partial f partial y is 0. But we do have the second derivative terms. So we have three terms. You can think of is 1/2 fxx, 1/2 fxy, 1/2 fyx. But because the 1/2 fxy and the 1/2 fyx, they're the same, mixed partial derivatives are the same, so that we can combine them, we just get one copy of fxy. Okay, so it's still the function value plus the second derivative over 2 factorial times the factor to the power 2. Okay, and here if it's xx, then we have x minus a to the power 2. If it's xy, then we have a linear factor in x, linear factor in y. If it's yy, then we have the linear factor y minus b to the power 2. So far, so good, everybody. So the rule is quite similar as before, right? Okay, now let's look at the graph. So this quadratic approximation is actually a quadratic function, right? We can draw a quadratic function in space. Okay, so we can see this is a graph. If we use a quadratic approximation, this is a paraboloid, right? And here you see this gives us another paraboloid, and we can tell this is a local max, and this is a local mean, and this guy we have a saddle point. So far so good. Okay, now let's look at the Hessian and the quadratic approximation. So we will use the determinant of the Hessian to analyze critical points. So we use D to denote the determinant of this Hessian matrix. Okay, so cross multiply fxx times fyy minus fyx times fxy. But because they're the same, so we just get fxy squared. So far so good, everybody. Okay, how would this relate to our maximum or minimum? So let AB be a critical point of the function. One can show the following facts about the quadratic approximation near the point. Okay? If the determinant of the Hessian, okay? So if the determinant of the Hessian is positive, then the graph is bowl shape. Okay, if the determinant of the Hessian is negative, then the graph of the quadratic approximation is saddle shape. So bowl shape, it could be a bowl on top or opening on top, or a bowl opening at the bottom. Okay, saddle shape, something looks like this. Right? If the determinant of the Hessian equal to 0, then the graph of a quadratic approximation is either a horizontal plane or a froze shape. Okay, horizontal plane or a froze shape, something like this. Okay, and here is the second derivative test for the function with two variables. Let AB be critical points of f. If the Hessian, the determinant of the Hessian is positive, so let's from now on, let's just call it D, okay? If D is positive and fxx, so partial f, partial xx is positive, then AB is a local minimum. Okay, I would, so let's listen to this rule. I will tell you how to understand this or memorize this. Okay, if the D is positive and fxx is negative, then the point AB is local maximum. If D is negative, then AB is a saddle point. If D is 0, then the second derivative test is inconclusive. Okay, so here comes the geometric meaning of the determinant of the Hessian matrix. Okay, if D is positive, so we know it's a bowl shape. So which means the graph, okay, is concave up in all direction, or the graph is concave down in all direction, right? The bowl shape, Okay, it's concave up in all direction. The bow is upside down, then it's concave down in all direction. So it is enough to look at the concavity of one particular direction. That's why it's enough to look at fxx. So what's fxx means? Well, it means you look at you have your surface, right? And then you look at in the x direction. So you want to look at, you use a plane to intersect, and then you can see here this guy, this curve, concave down, right? So that's why this is if fxx is negative, then this guy is concave. This curve concave down. Oops, right. Concave down. Okay. And if you look at the D, okay, if you look at the D is fxx fyy minus fxy squared. So if D is positive, it means the term fxx fyy is bigger, is positive. So fxx and fyy, they're in the same sign, right? So if fxx is positive, fyy is also positive. So if you want to look at the curve in the y direction, it's also positive. So we have this guy positive and that guy positive together give us a bow open up. Right? If both of them are negative, if this is negative and in the x direction is negative and the y direction is negative, which means they both concave down, and then we have a bow opens down. So far so good, everybody. Okay, let me see. This is x direction. Okay. If D is negative, that means the graph is concave up in some direction and concave down in some direction at AB. So AB is the saddle point. Okay, so if D is positive, then the concavity in all directions are the same. So you just look at one direction, for example, fxx. If it's positive, then the bow is like opening up. We have local minimum. Okay, if fxx is negative, then the bow is opening down. Okay, then we have a local maximum. If D is negative, so the concavity in different directions are different. Some directions concave up, some directions concave down. So we have a saddle point. If D is 0, this test, secondary test, is inconclusive. We must find some other methods. Okay, so usually the method we find is we pick some points near the D, and we want to show whether those points are all less than equal to that point, the values at that point, or the values of the other points around it are higher or equal to the values at that point, or maybe some values are higher, some values are lower. Okay, or then we can know whether it's a local max, local min, or a saddle point. All right, let's look at some examples. So we have some basic examples. Okay, first, we want to find the gradient. Okay, what's the gradient? What's partial f partial x? Well, that's 2x. How about partial f partial y? 2y. So what is the critical point? You set this guy equal to 0. So 2x equals 0, then x is 0. 2y is 0. We have y is 0. What happened? Why they move my stuff? That's interesting. They don't like my comma. Okay, let me fix it. So the critical point is 0, 0. Okay, so what is the Hessian matrix? Well, Hessian matrix fxx. So we take the derivative of 2x with respect to x, we get 2. Fxy, take the derivative of 2x with respect to y is 0. And this is 0 as well. Take the derivative of 2y with respect to y is 2. Okay, now what is D? D is the determinant of the Hessian matrix. 2 times 2 is 4. Well, this is positive. And then what is fxx? Well, fxx at the point 0, 0 is 2. It's also positive. So we know it looks like a bowl and it's concave up, right? It's a bowl concave up. Then we have local minimum. So far, so good, everybody? All right. Let's look at the next example. Minus x squared minus y squared. What is the gradient? Well, we have minus 2x, the derivative with respect to y, minus 2y, and set this guy equal to 0. That will give us x is 0 and y is 0. So what is the Hessian? Well, derivative of negative 2x with respect to x is negative 2. Derivative of negative 2x with respect to y is 0. And then this is 0 as well. Derivative of negative 2y with respect to y is negative 2. And then D, what's the determinant? Negative 2 times negative 2 minus 0, right? We get 4. But what's fxx at 0, 0? We get negative 2 is negative. So we have concave down in the x direction, then it's concave down everywhere because it's a bowl shape, right? D is positive. Then this guy is a local maximum. Alright, let's continue. So I really hope that you can, like for this easy examples, you can pause the video and try to finish them and then check your answers, okay? So this is 2x minus 2y, and when you set it equal to zeros, you have x is 0, y is 0, and then derivative of 2x with respect to x is 2, then derivative of 2x with respect to y is 0, derivative of negative 2y with respect to y is negative 2, while D is then 2 times negative 2 is minus 4. Negative. Okay, then we know in some directions concave up, in some other directions concave down, so this is a saddle point. So far, so good, everybody? Okay, let's continue. Let's consider similar surfaces that are flatter at 0, 0. What happened when we try to apply the second derivative test? Well, look at this guy. Derivative, we have 4x cubed, right? 4y cubed. When you set it equal to 0, we also get x is 0, y is 0. But here, what happened to the Hessian matrix? Well, derivative of 4x cubed, take the derivative with respect to x, we get 12x. It shifts my letter again. So what's the Hessian matrix now? (12x squared 0, 0) 12y squared, and then the D equals 12 times 4, 12, 144 x squared y squared. But you can see when we plug in D as 0, 0, we just get 0. So the second derivative test is inconclusive. Okay, but we know x to the 4th is looks like a parabola. It opens up, right? And then plus y, so it also opens up. So compared to a parabola, it's more flat at the bottom. So we know this is the local minimum. Okay, well this guy is the similar picture, but now we have open down, right? And so we know this is a local maximum. And then let's see, the gradient will be minus 4x cubed minus 4y cubed. Critical point, we set the gradient equal to 0, we also get the 0 vector. And now the Hessian is minus 12x squared 0 0 minus 12y squared. And the D is still 144x squared y squared. And D, when we plug in 0 0, is still 0, so it's still inconclusive. But we can see this is a local maximum. And actually this guy is a saddle point. Okay, because in the x direction it opens up, in the y direction it opens down, so it's like a saddle point there. Then this is 4x cubed minus 4y cubed. When we set it equal to 0, we also get 0 0. The Hessian, we get 12x squared 0 0 minus 12y squared. And you can see D is minus 144x squared y squared. But when we plug in 0 0, it's still 0, so it's still inconclusive. Okay, so we can see if it's flatter, the surface is flatter, then the second derivative test does not apply here. Okay, let's continue. In that case, it's better to draw the surface to decide whether it's a local mass, a local mean, or a saddle point. Okay, so let's look at the following example. So this is a typical example I will ask you in the exam. So I give you a function in two variables, and I ask you to find all maximum points, local minimum points, and the saddle points. Okay. So first, we need to find the critical point. So what is fx? Derivative with respect to x, we have 4y, y squared, and 2x. So far, oh, my 4 looks like it. Okay, let me rewrite it. So far, so good. And fy equals 4x, 2xy, and that's it. So far so good, everybody. Okay, we want to set it equal to 0. So we have a system of two equations, but they're not linear. Okay, so how do we solve this kind of we look at the pattern of each equation. Okay, the second equation looks more simpler. Okay, so let's look at the second equation. You see, we can factor it. We can factor 2x, and then we have 2 plus y equals 0. That means either x is 0 or y equals minus 2. Okay. Oh, so far so good. Okay, so if x equals 0, plug in the first one. Okay, so here we're using substitution method, right? We find some pattern, and when you try to like solve equations, move all the terms on one hand side and try to factor it. Okay, and then you look at different cases that each factor equal to 0. So if x is 0, we plug in 1, we get 4y plus y squared equals 0. Alright, we can factor out the y. We get 4 plus y is 0. So we have y equals 0 or y equals minus 4. So this gives us 2 points, 0, 0 or 0, negative 4. If y equals negative 2, then we plug in 1. We get 4 times y, 4 times negative 2, negative 8. Negative 2 squared is 4, minus 2x is 0. So move 2x to the other side, minus 8 plus 4 is minus 4. So x is minus 2. Well, in this case, x is minus 2, y is minus 2. We get 1 point. So we get 3 critical points. 0, 0, 0 minus 4, minus 2, minus 2. Okay, sometimes when you solve the system of equation, you might find many critical points. And then on each critical point, we need to test the D. Okay, so let me use a different color here. So fxx is, well, take the derivative with respect to x. We have negative 2 fyy. Take the derivative of fy with respect to y. We have 2x. fxy. Take the derivative with respect to y. 4 plus 2y. Okay, so what? Let's see here. So our Hessian matrix equals negative 2, 4 plus 2y, 4 plus 2y, and 2x. So let's look at 0, 0. Okay, D is the determinant of the Hessian matrix minus 2. Well, when y is 0, this is just 4. When x is 0, this is 0. So we have negative 2 times 0 minus 4 times 4. We get negative 16, negative. Then we know this is a saddle point. Okay, next, at 0 minus 4, we have D is negative 2. 4 minus 8 is minus 4. X is 0. Okay, minus 2 times 0 minus negative 4 times negative 4 still 16, right? Negative 16 is still negative. I don't have enough space. Let me put it here. So this is still a saddle point. Okay, last point at negative 2, negative 2. Well, then D is negative 2. Okay, 4 minus 4 is 0. 2x, now minus 4, right? So minus 2 times minus 4 is 8. 8 is positive, but fxx is minus 2, negative. So it's like a bowl shape, but it's open down, it's a concave down. So we get a local maximum in this case. So far so good, everybody. Yeah, so this is a typical example of, like, we have a function, and then first step we find the critical point. So we calculate the first partial derivatives and set it equal to 0. Then we need to solve the system of equations. Compare each equation, find the easier one, try to factor it. Okay, so make sure right hand side is 0, and then on the left hand side try to factor it. And then we can divide into different cases and then plug in the first equation to solve. Okay. Sometimes if you can use, let me see. If you want to use substitution method, then you can express x in terms of y and then plug into the other equation, or express y in terms of x, plug into the other equation. So after you solve and find the critical points, then you're gonna calculate the second partial derivatives, and then at each point you're gonna compute the D. D is the determinant of the Hessian matrix. Okay, and then you depends on the rules, whether D is positive or negative, whether fxx is positive or negative, then you know whether it's saddle points or local max or local min. Alright, so you have a lot of examples on your homework that you can practice. Let's look at the following example. So consider the function f of xy equals y cubed minus x squared y. Show that 0, 0 is the only critical point. Okay, so let's find fx and fy, the gradient, right? So partial f, partial x. Take the derivative with respect to x. We have the first term, no x gone. Derivative of x squared is 2x, so minus 2xy. Derivative of f with respect to y. The first term gives us 3y squared. Second term, we have negative x squared, right? So we set it equal to 0. Now, let's look at, I would say let's look at the first equation. It looks easier, right? So minus 2xy is 0, then it means x is 0 or y is 0. So we have two cases. If x is 0, plug in the second equation, we get 3y squared is 0, so y is 0. So we get the critical point 0, 0. If y is 0, plug in the second equation, we have negative x squared is 0, so it means x is 0. So we also get the same point. Okay? So that's why 0, 0 is the only critical point. That is part A. Part B, apply second derivative test to classify 0, 0. And what happened? Okay, let's find fxx. So derivative of negative 2xy with respect to x, we have negative 2y. fyy, take the derivative of that with respect to y. 6y, because x squared has no y, so it's gone. fxy, take the derivative of negative 2xy with respect to y. We have negative 2x. So the Hessian matrix equals negative 2y, 6y, 6y, negative 2x. Okay, so at 0, 0, okay, D is, well, the determinant when you plug in x, y, 0, it's just all 0. We get the D is 0. What happened? The second derivative test is inconclusive. So, okay. And now, part C. Notice that f of 0, 0 is 0. Oh, why is that? Let's change a different color. Okay, so what is f? This guy, y cubed minus x squared y. When we plug in 0, 0 cubed minus 0 squared times 0, yeah, 0. Yeah, so f of 0, 0 is 0. We check that. Draw the level sets of fxy equals 0 and indicate your picture where f is positive and where f is negative. So f level sets f of xy equals 0, y cubed minus x squared y. Okay, keep that in mind. Y cubed minus x squared y. Okay, what's the level set? What's the common factor? Y. And we have y squared minus x squared. We can factor further. Y plus x, y minus x. Yes. So we have y equals to 0, or y plus x is y plus x is 0. It means y equals minus x, or y minus x is 0, so y equals x. Okay, so how do we draw the level set? Let's see here. Okay, so this is the x, this is the y. Okay, and what is y equal to 0? Well, y equal to 0 is the x-axis. Okay, and y equals minus x, well, that's the line passing through the origin with the slope negative 1. What is y equals x? This guy with the slope is 1. So this is y equals x, this is y equals minus x, this is y equals 0. Okay, so those are the three level sets, right? Okay, let's see the problem. What do we do next? Oh, we want to indicate in our picture where f is positive and where f is negative. Okay. Let me use a different color. Okay, let's use this color. So this is my f, right? Let's pick some point here. We know this. Let's say this is 1, 1, and this point will be 2, 1. Okay, so f of 2, 1 is I want to. Oh, I don't have enough space. Okay, let's do it here. So 2. X is 2, y is 1. Then we have 1 minus 2 squared, which is 4, times 1 is negative 3. Okay, so in this whole region, if one point gives us negative, then the whole region is going to be negative. Let's look at this point. This point is 1, 2. When we plug in that, f of 1, 2 equals y is 2, 2 cubed is 8 minus 1 squared, 1 times 2, 2, 6. See, it's 6. So it's positive, so good. So actually this region and you know this whole region are together, then we know that the whole region is positive. Okay, you can also put this point and see whether it's positive. Okay, and here we can pick negative 2, 1, negative 2, 1. Then the y, we have f is 1 minus negative 2 squared is 4. We still have negative 3, so this is negative. Okay, how about the next one? How about negative 2 and negative 1? Well, let's see. Negative 1 cubed is negative 1 minus negative 2 squared is 4 times negative 1 is plus 4. So we have 3. Oh, so this region is going to be positive. And similarly, let's see here. Okay, here we can pick this point is easier because we know this whole region is gonna be of the same sign, right? And this is 0 minus 1. Y is minus 1. X is 0. Ooh, good. So you see, this is negative. Here we can pick this is 2 minus 1. Y will be y cubed is minus 1, then minus 2 squared is 4, 4 times minus 1. Oh, negative become positive. So we have 3. So 3 is positive. Now you can see some region f is positive, some region f is negative, and at the origin f is 0. Then what can you tell? Right, part D. Use the information we find in part C to definitely classify the critical points. So we know it's a set of points because near it, some points is higher but bigger equal to it, and some points is smaller than it, right? Has the function value smaller than it. So we know that 0, 0 is a saddle point. Okay, because near it, near 0, 0, some point is we can say, okay, okay, f of near that point, f of xy is positive for some points, and fxy is negative for some points, right? Okay, no matter how close to it, we can always find some point that is positive, that has the function value is positive, and we can also find some points that have negative function values. Okay, so that's why 0, 0 is a saddle point. So far, so good, everybody. Okay, so this is session 12.8, And please do your homework. I gave you many examples in the homework, so please practice. Especially the skill of solving a system of equations, because we're solving system of nonlinear equations. So in general, it's harder. It depends on the problem, the method, or which equation we choose to look at is gonna be different. Okay, so I really hope that you can have more practice about this session. Okay, so if you have questions, feel free to print screen your questions and email me. Have a nice day, or ask me in my office hours. Okay, or yeah, ask me in class. Okay, have a nice day. Bye.